Hello everyone, I am Hanan Rizk, a master student from Grenoble Alpes University. Today I am going to give a presentation on the optimal control for partial differential equations of a heat exchanger system. As we know, the double pipe heat exchanger is a device used to perform the process of mixing fluids having different temperatures, which is very common in the industries of oil refinery and food, and an important component in many installations types like heating, air conditioning, and steam power labs. The high effectiveness of the counterflow heat exchanger makes it one of the most popular types of this heat exchanger system device. Besides that, the double pipe heat exchanger, which is very suited for high pressure and temperature applications and low flow rates, can be used in the applications of a small heat transfer surface because of its small amount of heat transfer per section. Today, we face many problems in the heat exchanger system because of the increase in the temperature. In fact, because the failure of the heat exchanger is being extensively experienced by the chemical process industries, and a loss of production can be made for a long time due to this failure. Moreover, credible events such as fire, explosion, and toxic release can be happened due to loss of containment through the heat exchanger, and most of its accidents result from excessive temperature rise. Hence, the system safety of the double pipe heat exchanger depends on the behavior of the temperatures of the hot and the cold fluid, which is modeled by two first-order coupled hyperbolic partial differential equations, as we will see after, that represent this complex system we handle. Our control objectives are the safety of the heat exchanger system and the performance and the description of the temperature profile, which is the main parameter to be controlled in the heat exchanger system to solve and to face the previous mentioned problems. Briefly about the structure of our work. The first step, I would like to tell about the system presentation and our objectives of this work. The next step, it's about the control design procedure, and in the end, general conclusions and some proposed points to improve this work. Based on some certain assumptions and this simplified model of the heat exchanger system, which shows that the heat exchanger system type we handle in this work is counterflow, where the flows are in opposite directions. The temperature dynamics of the heat exchanger system are given by two first-order coupled hyperbolic partial differential equations, as we see in this slide. The system parameters are considered known and constant. This system has the boundary conditions U1 and U2 and the initial conditions T hot node and T cold node, and the system outputs are Y1 and Y2. Our objective from this work is to present the optimal control of a double pipe heat exchanger system which is a complex system modeled by two first-order coupled hyperbolic partial differential equation based on the adjoint method calculus of variation. We propose a gradient descent algorithm which is easy to understand and implement and whose convergence is very ensured. To solve this control problem of this heat exchanger system we handle, our simulation results, which have been obtained based on the experimental values of the hot flow and the cold flow temperatures, making the study more realistic and easy to be validated in practice, show the effectiveness of the proposed algorithm and the optimal control approach to solve the optimal control problem of the heat exchanger system and to control the temperatures of the hot flow and the cold flow along the pipes of the heat exchanger system, and the safety of both heat exchanger system and the performance. In addition, this work activates and boosts the role of the application of the adjoint method calculus of variation on a complex system like the one we handle with smooth results and the flexibility of the proposed algorithm to be improved for future work. So, in this section, we will design optimal control for the heat exchanger system through the following steps: deriving the necessary condition of optimality using calculus of variation, solving the system PDEs and the adjoint PDEs using the method of line, proposing gradient descent algorithm to solve the optimal control problem for the heat exchanger system, which is proved its effectiveness through the results we will show after. This is the optimal control model of the heat exchanger system. It's an optimal tracking problem boundary control case formulated as we see, subject to the temperature dynamics of the heat exchanger system, which I have mentioned before. The objective here is to determine the control variables U1 and U2 to minimize the performance index or the cost function J, our objective function J, and satisfy the constraints which are represented in the temperature dynamics of the heat exchanger. In order to derive the necessary condition of optimality for the optimal control problem, according to calculus of variations method, the solution of the optimal control problem of the considered heat exchanger is determined by minimizing the Lagrangian defined by introducing the constant variables B1 and B2 to transfer the constraints which are represented by the temperature dynamics as I mentioned in the previous slide, to transfer these constraints to the cost function as we see in the Lagrangian formulation. After that, we will use the integration by parts with respect to time and space for the hot and cold flow, and computing the directional derivatives for the hot flow and the cold flow. Now we obtain the necessary optimality condition of the optimal control problem for the heat exchanger system we handle, which are represented in the adjoint equations with its boundary conditions and the final conditions, and the optimal inputs U1 star and U2 star, and the forward equations which are represented by the temperature dynamics of the heat exchanger system with their boundary and initial conditions. Next, we will solve the system PDEs and the adjoint PDEs using a method of lines. In order to solve the forward equations using a method of line, the first step is to use the finite difference approximation as we see in this slide for the hot flow and the cold flow. And the first partial derivatives can be approximated as we see for the hot flow and the cold flow. It's more convenient to write the system in the standard form, so-called linear parameter varying system, like the state space model of the system. Next, we define the matrix A and B, and to improve the clarity of the exposition, we will try to represent the large messy terms with either terms as we see from A1 to A4. In the end of this section, we get the system states T hot and T cold. Now, in order to solve the adjoint equations of the heat exchanger system using a method of line, we will follow the same sequence as I explained before for the forward equation. The first step is to use the first difference approximation, and the first partial derivatives of the adjoint PDEs can be approximated as follows. As we see here, by substituting with these two equations for the first partial derivatives after their approximation with the finite difference approximation in the adjoint equation of the system, it's more convenient to write the system in the standard form, so-called linear parameter varying system. Next, we define the matrix M and F. In order to improve the clarity of exposition, we will try to represent the large messy terms with either representation, as we see from M1 to M6 and from F2 to F3. At the end of this section, we get the constant variables B1 and B2. Now, we derived the necessary condition of optimality using a calculus of variation and solved the system PDEs and the adjoint PDEs using method of lines as we see before. Now we define a gradient descent algorithm to solve the optimal control problem, which can be summarized in the shown 5 steps. Based on the main principle of operation, physics, safety and stability requirements of the heat exchanger system, it can be seen from the temperature dynamics along the tubes with initial condition too hot 70 degree and too cold 20 degree. and the temperature dynamics along the tubes with Gaussian distributed initial conditions shown in this slide. The effectiveness of the proposed optimal control approach and that the optimal inputs are able to control the temperatures of the hot and the cold fluids along the pipes of the heat exchanger system in an effective manner. Let's conclude. In order to solve the optimization problem for a double pipe heat exchanger system governed by two first-order coupled hyperbolic differential equations that we handle in our work, we first apply optimization and then discrete method for the optimal control problem of the heat exchanger system. Based on this, we propose a gradient descent algorithm to solve this problem. The proposed gradient descent algorithm in this work guarantees efficient temperatures control and the safety of both heat exchanger system and the performance. This work can be improved by these proposed points by validating the simulation results reported in this work, which are performed successfully, and to test the performance of the proposed optimal control approach in practice. An interesting extension to this work is to test alternative efficient numerical methods other than the iterative time-consuming projected gradient descent algorithm to accelerate the computations and increase its chance of real-time implementation. Decoupling the two coupled hyperbolic partial differential equations modeling the heat exchanger system and applying this proposed control approach for comparison studies. And this is the experimental heat exchanger system that we would like to validate our simulation results on it in GIBS lab of Grenoble Alpes University. And these are the main results we used in this work. Thank you for your attention. For any questions, you can send me email. Have a good day.